In this video, I will be discussing topic 12A of Edexcel IAL Chemistry, and topic 12 is basically entropy and energetics, and 12A would be entropy, and 12B would be energetics in terms of lattice energy and solubility and etc. Okay, so let's get started. So endothermic reactions, this is the energy diagram for the endothermic reaction. For endothermic reactions, they're thermodynamically unfavorable because the delta H is positive. So we're going from a lower energy level to a higher energy level. So the products are more energetically unstable than reactants. So yeah, over here, let's read that through. Products are at a higher energy level than reactants, meaning they are more unstable than reactants. But endothermic reactions still occur, and we have an example over here, cold packs. So how they work is actually NH4NO3, which is ammonium nitrate. It is separated with water by a thin membrane. When they meet, the temperature is going to decrease because the endothermic reaction occurs, and that's how cold packs work. So they occur spontaneously. So there must be a different aspect to consider when determining the spontaneity of reactions, and that is where entropy comes in. Entropy is the measure of disorder of a system, and it's favorable for more disorder. So more randomness, the better. So it's also known as the number of different arrangements of molecules possible in a system. Okay, so let's discuss further. So entropy will be increasing as you go from solid, liquid to gas. So the reason why the entropy increases is because the arrangement of molecules in solids, liquids, and gas is becoming more random as you go there. So let's take ice for an example. Ice is solid, right? And it's going to melt spontaneously at room temperature to become liquid. And eventually the water is going to start evaporating into gas. And it's favorable that it happens, right? And one thing to add is that a perfect crystal at 0 Kelvin has 0 entropy. And I'm hoping that you know 0 Kelvin is basically minus 273 degrees Celsius. Okay, and so another phenomenon that happens over here is that when you spray perfume from a corner of a room, it's going to just start diffusing, right? Diffusing across the room. And it's going to increase in randomness of arrangement of the gas particles, basically. So this is a positive entropy change as well. So entropy change, this is delta S. That's just literally entropy change, right? Entropy is S, and then the delta stands for the change. So, okay. The next one is dissolving an ionic lattice. So, we have a solid ionic compound over here where ions are regularly arranged in a solid lattice. But when we dissolve this, ions dissolved are randomly arranged in between solvent molecules, right? So therefore, randomness has increased as we dissolved the ionic lattice. So the delta S, the entropy change, is going to be positive from a lower entropy value to a higher entropy value. Okay? And now we're going to discuss something called delta S entropy change of a reaction. It's also called delta S of system. So for example, we have A and B as our reactants, and we have C and D as our products. We have 2 A molecules and 1 B molecule reacting to give 3 C molecules and 2 D molecules. So let's look at the change in the numbers of molecules. So we have 3 molecules on our reactant side, and we have 5 molecules on our product side. So the number of molecules is increasing, right? And that gives increasing number of arrangements possible, and therefore the entropy is also going to be increasing. So the change in entropy is going to be positive from a lower to a higher entropy value. Okay? So not only do we have the entropy of the system, we're going to have something called a delta S surrounding. So this is basically the surrounding molecules may be involved in some energy transfers while the reaction is occurring. So around the reactions, there might be gas molecules or liquid molecules if the reaction is inside a solution, gaining energy or losing energy, okay? Depending on if the reaction is exothermic or endothermic, right? So entropy change the total entropy change can be calculated by taking into account the delta S of system and delta S of surroundings. So delta S of surrounding, entropy change of the surroundings is basically the energy transfer to the surrounding molecules from the reaction, and we have the entropy change of the system, which is basically the entropy change of the reaction occurring. So it's a difference in entropy of the reactants and products, okay? So the delta S of system can be calculated from the sum of the entropy of products and the sum of the entropy of the reactants. Obviously, the product is going to be what we're left with, basically the final products. So we need to do that minus the entropy of reactants, okay? And we can calculate delta S surroundings by this formula. So it's minus enthalpy change of the reaction divided by temperature in kelvins. It's not in degrees Celsius. If the question gives you the temperature in degrees Celsius, you must change it into kelvins by adding on 273, okay? So we can also just extend that delta S total formula because we can substitute these, right? So we have entropy change, the total entropy change equals brackets, we have the products minus reactants, and then we have the delta S as surroundings being calculated with minus enthalpy change divided by T, temperature. So if there's a rule over here, if the total entropy change is positive, we say that the reaction is feasible, okay? So we're gonna look at some questions. Here, this question is about the thermodynamics of the reaction. Thermodynamics meaning basically the entropy change. So we're given the standard molar entropy of the reactants and products. We have N2O4 gas going into 2NO2 gas molecules. And the enthalpy change is positive 57.2 kilojoules per mole. So that is an endothermic reaction. So we have our standard molar entropy as 240 for NO2 and 304.2 for N2O4. We also have the standard molar enthalpy of formation for NO2 is 33.2. So what we need to do first is calculate the entropy change for the reaction using the information in the table, including a sign and units in your answer. So we have delta S of system, which is basically calculated with the entropy of products minus entropy of reactants. So we have the entropy of product, which is 2NO2, right? So we need to times 240 over here by 2. So we have 2 times 240 being subtracted by the entropy of reactant, which is 304.2 in this case. So overall, we should be able to get the answer as 175.8 joules per Kelvin per mole, okay? So joules per Kelvin per mole is the units, okay, for entropy. And the next question is calculate the enthalpy change of formation of N2O4 gas at 298 K using the information in the table and the enthalpy change of reaction. Include a sign and units in your answer. So first of all, if we go back, this was the missing value, right? We're trying to calculate this one. and we're given the formation enthalpy for NO2, which is 33.2, and we have the enthalpy change of the reaction 57.2 kilojoules per mole. So we can start labeling some stuff in our cycle. So the way I kind of figured out what we need over here is because we're working with delta H formation, right? And we're trying to find one delta H formation, delta formation F in this. Yeah, and we have, on top is just going to be our reaction. So after I've labeled everything, basically, we have 57.2 going that way, and forming from our elements in their standard states, we're forming 2 NO2, so we need to times 2 the enthalpy change for formation of NO2, and this is the value that we need to calculate, and this is the overall arrow basically going that way, because this arrow is what we need to find out what's happening, right? So yeah, that is the overall direction. So we're going along this arrow like this, but we're going against this arrow. We're going against that arrow. So we shall be flipping the sign for this, right? So we would have to just add this value over here, and we would have to subtract this value because we're going against this direction, right? Yeah, so we have overall the delta FH being plus 9.2 kilojoules per mole, okay? So try the calculations yourself as well, okay? You can pause the video before me explaining, so you can try yourself as well. So calculate the entropy change for of the surroundings, delta A surroundings at 298K. Give your answer to appropriate number of significant figures. Appropriate number of significant figures is basically the same number of significant figures the question uses most commonly, or basically just 3 significant figures most of the time. It's just not sensible to give around 6 significant figures. So yeah, first of all, I'm going to write down the formula for delta S surroundings, which is basically minus delta H, the enthalpy change of the reaction, and then the temperature T. So delta H is in kilojoules per mole, right? The units for delta H. But delta S is in joules per Kelvin per mole. So from kilojoules per mole to joules per Kelvin per mole, you would have to times it by 1,000, right? We need to get rid of that K prefix. So yeah, if we do the calculation, so we have already calculated 9.2 from our previous question, right, as the enthalpy change, and we're going to times it by 1,000 because obviously we need to change kilojoules into joules, and then we're going to divide it by the temperature 298K, okay? Then you should end up with minus 191.946 joules per Kelvin per mole, okay? And then the next question, use your answers to part A and C to calculate the total entropy change, delta S total, for this reaction at 298K. So the formula for delta H, the total entropy change was delta S system plus delta S surroundings, right? And system was basically products minus reactants, and then surroundings was delta H divided by T, which we already have calculated. So we have calculated in A, we had 175.8 from part A, right? And 191.946 from part C, and we can just add that up, and we will be ending up with minus 16.1 joules per mole per Kelvin. And what can we tell from a negative value of entropy change, the total entropy change? It's negative, right? So it's not going to occur spontaneously at the specified temperature, which is 298K in this example, okay? If it's positive, it's feasible, right? But if it's negative, it's not feasible, okay? And the next question, this reaction can also be written as an equilibrium. So this is the reaction, but the delta H is basically the same, which is going to be plus, what was it, 57.2? Yeah, and the reaction, the formula is going to be just total entropy change equals delta S system plus delta S surroundings. So when we want to calculate the temperature where delta S total is 0, right? So we need to give delta S as 0, okay? And we know the delta S system, which was 175.8. This is just a difference between the entropy of the products and the reactants, right? And this was calculated from part A. And we have the delta H over here substituted times by 1,000. We need to times it by 1,000 because the 57.2 is in kilojoules per mole, right? Whereas the delta S entropy values are in joules per mole per Kelvin, right? So we need to change that. That's why we do a times by 1,000. And we have to divide that by the temperature, which in this case, we want to get, right? So we're going to basically rearrange this in order to make T as our subject, and you would end up with 57.2 times 1,000 divided by 175.8, okay? And you will end up with 325.37 Kelvin, where this reaction basically can occur. It's feasible at this temperature. Feasible. All right, we have a different concept, not a different concept, but another concept that we need to discuss. Thermodynamic stability versus kinetic stability. So we've learned that if delta S total is positive, the reaction is feasible, right? But that's not kind of all in reality. So let's discuss this reaction over here. This is an exothermic reaction energy diagram. So from reactants and products. So the delta H is going to be negative, the red arrow going down, because this is an exothermic reaction. But we can also see that the activation energy is pretty high, right? Over here, the blue arrow is going to be our activation energy. Although reactants are thermodynamically unstable compared to the products, so the reactants are higher in energy level than the products, meaning that it's pretty unstable. They're kinetically stable though, due to the high activation energy. So if we don't provide them with the activation energy required for the reaction to go on, the reaction just wouldn't occur. So we call that reactants are kinetically stable, okay? So the reaction might still just not go on, even if it's exothermic, okay? Yeah. Which means that the reaction will not occur if activation energy is not provided initially. So therefore, thermodynamically feasible reactions, like when delta S is positive, it may not occur spontaneously still at a specific temperature due to the high activation energy, okay? This is the key concept over here, high activation energy. And let's try more questions. So we have B1. Some data about nitrosyl chloride is given in the table. Complete the table with data for nitrogen 3 oxide and chlorine. That's the oxidation state of nitrogen. We have N3 plus inside there. And chlorine using the data booklet where appropriate. So these were taken from basically the data booklet. Obviously, the enthalpy change formation for chlorine gas is just 0 because that's already in its elemental state and in its standard state, the gaseous Cl2 molecule. And part 1 is just done because it's just from the data booklet. And part 2, calculate the standard enthalpy change of the reaction, delta H at 298 K. So we have this overall reaction, and because we're working with delta H of formation, we're going to put our elements in their standard states in the bottom. So we have nitrogen gas, oxygen gas, and chlorine gas. Okay, so we're using these are our ingredients to make the reactants and products in this case, just using the cycle. So when we're forming 2 molecules of NaCl gas, the enthalpy change is going to be 51.7, this is taken from the table, times by 2 because we are making 2 of them, right? And on the right over here, making the products, we have to times 90.2 by 2 because we're making 2 NO gas, and we're not going to write anything for chlorine because it's just 0. Yeah, and the overall reaction is going that way. So we're going against this arrow and along this arrow. So we need to flip the sign for this part, but just take this part. So I have put the negative sign over here. 2 times 51.7 plus 2 times 90.7, and we're going to end up with 77.0 kilojoules per mole. We can tell that this reaction has a positive enthalpy change, so it's an endothermic reaction. Okay, so to the next. Use your answer to BII to explain why delta S total becomes less negative as temperature increases. So when you're tackling these kind of questions, you're going to first of all just write down the formulas, okay? So let's write down delta S of surroundings is equal to minus delta H divided by T, and delta S total is basically the sum of delta S system and delta S surroundings, okay? And so our delta H value is positive, right? Which is endothermic. So if the temperature is increasing, the delta S surrounding becomes less negative. So when the denominator is increasing, this whole thing is going to be contributing less to the delta S total, right? Therefore, delta S total also becomes less negative, okay? If the negative value is getting smaller, then the delta S total is going to also be less negative, right? Yeah, that's how you can tackle these kind of questions. And moving on to the next. So give the expression relating the equilibrium constant to the total entropy change, and hence explain how the equilibrium constant changes as the temperature increases. So this formula here, this is actually going to be in equilibria, chemical equilibria, which is topic 13. But there are many questions that relate these two equilibrium constant and delta S total. So this is the formula that you will be learning in chemical equilibria. So delta S total is also equal to R ln K. So initially you learned that delta S total is directly proportional to ln K, and R is going to be our constant, which is the gas constant, okay, which has a fixed value of 8.31 joules per Kelvin per mole. So when temperature increases, delta S total increases, and so K is also going to increase, which means that the equilibrium will shift that way, and you will probably see in detail why that happens in chemical equilibria. Okay, so I'm just going to leave that one there. CI, the standard molar entropies of the substances S in the reaction are given at 800 K. So we have a very high temperature, 800 K. Explain why the values for the standard molar entropy of all these substances is greater at 800 K than 298 K. So first of all, the kinetic energy of each particles is greater, right? So, which means that there's going to be more random movement of particles at a greater speed even. So that increases in randomness, right? And also the second factor that you want to take into account is over here. This is the Maxwell-Boltzmann distribution of energy, the energies of molecules. Basically, this is the y-axis of number of molecules, and this is the x-axis for energy, the molecular energy. So at 800 K, the orange line over here, the Maxwell-Boltzmann curve is more spread out, right? Meaning that there is more randomness of energy distribution. And yeah, so that is why it's also increasing in randomness, okay? So therefore, the entropy values are going to increase, okay? Yeah, let's do some more questions. Calculate the entropy change of the system at 800K. This is just the products minus reactants like we did before. And if you just plug in all the values from the values given over here, we have the values given over here. Just plug in the values according to the reaction. We get 189.3 plus 2 times 231.2. These are products. And we have the reactants over here. So the delta S system is going to be 40.7 joules per Kelvin per mole. And the standard enthalpy change of the reaction, delta H, at 800K is 53.2 kilojoules per mole. Show by calculation whether or not the reaction is thermodynamically spontaneous at 800K. So spontaneous means that delta S total has to be positive, right? So we need to determine that. So first of all, we're going to calculate our delta S surroundings, which is involved in calculating delta S total, just as the formula stated. So we're just going to plug in 53.2 in there, and we have times by 1,000 because obviously the units, right? And divide by 800K. Because that's the temperature, and we get minus 66.5 joules per Kelvin per mole. And we're going to just put that into here. So that was delta S surroundings, the delta S surroundings and delta S system we calculated in the previous question. What was it? Oh, it was this one. Yeah, that one is going to be in that bracket, and therefore you get minus 25.8 joules per Kelvin per mole. So this is negative, right? So it's not going to be spontaneous even at 800K, which is a very, very high temperature. Okay, that was the end of the questions that I wanted to go through. So yeah, I hope you found this helpful, and I will see you in the next video.